It will do. So hey, pleasure to be here. I've had a really good conf so far, first MCubed. I'm Chris, and I work for Cloudera Fast Forward Labs. Cloudera, you may know from Hadoop fame, or you may not. Fast Forward Labs is a little bit of an odd duck in Cloudera, so we are their applied machine learning research group, and I am newly the research engineering lead. So we do a bunch of stuff, but maybe the most kind of eye-grabbing of that is write these capability reports on machine learning topics. So we stay up to date with the latest in industry and academic research, and then work out what's useful and what's work and what capability it gives you. Like, does the fancy math do a thing that is novel? So we have 12 reports at the moment. Number 13's a couple of months out. But today I'm going to talk about Federated Learning, which is number 9. So the report itself is only available to our clients. These are like corporate subscriptions. But with every report, we build a thing. And the thing that we built for Federated Learning is a little game that you can play in your browser, and that is free to everyone at turbofan.fastforwardlabs.com. I'm going to talk more about that later. The reason we build stuff is because we really want to understand like how the algorithm connects to, say, a business problem or like some output. And it gives us like actual credible expertise in building things with these systems. So yeah, go have a play. You can do so now if you want, but if you hammer the Wi-Fi, my talk might disappear. Cool. So by show of hands, who is paid to code? Like, some. Okay. So if you are like hands-on data scientist or machine learning engineer, then I hope that you come away from this kind of understanding what federated learning is and a bit about how it works. If you're more like in the strategic or business world, then hopefully I know you should come away knowing whether you might have a use case and whether it's worth investing in further investigations. So the menu is, I'm going to talk about what federated learning is and why you should care about it, or the circumstances under which you should care about it. I'm going to walk through a particular implementation or algorithm for it. And then we're going to talk about the prototype that I just showed on the previous screen. I'm not going to give a full demo of it because it takes 10 minutes, but I'd be happy to give one over coffee if anyone's like super interested. So then we're going to talk about challenges because there are no silver bullets that are associated with this kind of technique. And finally, I'll talk about the state of open source tooling for it. So why care about federated learning? Or like in what circumstances should we care? And also, what is it? Well, conveniently for me, my employer came out with this sort of marketing bit at the start of the year, where we talk about building the compute platform that takes you from the edge to AI for non-specific definitions of edge and AI. And that was super convenient for me because it lets me do this and say that federated learning is about taking AI to the edge, again, for non-specific definitions of both. To cease burying the lead, federated learning is machine learning on decentralized data. And I usually target this as being like the highest buzzword density sentence at any given conference. So I'll apply my buzzword removal algorithm and see if it makes any more sense. Let's make it a little bit more concrete. Federated learning is something that applies in a situation when we have data that is spread around a federated network of nodes. And we'd like to do smart stuff with it. Like we'd like to build predictive features or model it or learn something about it. But we can't access it. So I'm not talking about distributed around a network of nodes. Like these aren't different containers in your Kubernetes cluster. These aren't like different, like this isn't a Spark job that's being distributed like, with Yarn or something. A node might be a mobile phone or a vehicle or some IoT equipment in like an industrial setting or a health monitor. A node might be a browser. And there's data on it that we don't have access to. And there's a bunch of reasons we might not have access. Privacy, bandwidth, if it's generating a lot of data, all sorts like power consumption of the bandwidth of data transfer. But let's maybe make it even more concrete by talking about 3 kind of fictional but representative businesses that might be interested or find themselves in this situation. The first is like maybe we are Pear. Pear is a smartphone manufacturer that just released the Pear Phone 11 Pro with 3 cameras. And it wants to give smart features to its users. So you use those 3 cameras to take a bunch of pictures, and maybe you want to automatically create an album and remove duplicates and select like the most eye-popping pictures. We want to do predictive text. We maybe want to help our users write emails and elicit that are more likely to elicit a response with a grammar checker or something, or avoid spam filtering when they're legitimate. But the problem is that Pear set itself up as a very consumer privacy-focused company. And to do all of this, we need access to data. And there's a bunch of reasons our users might not want to give us that. Firstly, it's personal, it's private. And secondly, the most expensive thing you do on your phone is use data. Like the thing that drains the battery is sending stuff to some cloud and getting it back. So there's that concern as well. Maybe we deal with even more intensely private data. Maybe we're a health monitor company. I think we call it Nephrodine. Maybe we make embedded devices that live on people and track biometric signs so they can warn early of kidney failure. So firstly, we definitely need to be able to do, in this situation, inference on the edge. So we need to be able to predict on device, because I don't want my warning about kidney failure to be contingent on me having a signal. But moreover, storing that data is extremely highly regulated. So if I can avoid actually bringing the data back to my data center, then I'm doing the user a favor because I'm not invading their privacy or risking data loss to a third party. And I'm also doing myself a favor because I don't have to deal with so much of GDPR and HIPAA in the States. And the third and final example we'll give here is the one that we built a prototype around. And that is maybe I'm an industrial device manufacturer or user, and I have some jet engines or something, and I'm monitoring them. And when I'm doing that, some of these devices are monitored to the nth degree. I'm aware of industrial precision manufacturing equipment where every part has 4 cameras on it. That's generating a ton of data, and I don't want to stream it back to a data center. I might not even want to store it on device for that long, but I still would like to learn things like, when is this device likely to fail so it doesn't blow up? And if I'm the manufacturer of such equipment, I want to give my customers warnings about when they should maintain them. But they're not going to share their actual failure data with me because that's very private, sensitive, competitive information. So in all of those situations, all of those examples, we're in this situation where we have some data that's spread around a so-called federated network of nodes. And we want to do some smart modeling, but we can't just pull it all onto our data scientist's laptop and do it there. And I'm telling you that federated learning is the solution to that. And your intuition may be that there is some totally inscrutable math that underlies this. True. It's averaging. So in 2016, Google, who put out most of the papers on this stuff, put out this paper, Communication Efficient Learning of Deep Networks from Decentralized Data. I don't know how I use the light. Oh, well. As an aside, if you are someone who doesn't read a ton of papers, or maybe like the situation I was in a couple of years ago where you don't read a ton of papers anymore, this is a really friendly paper. It's really good systems level thinking, something I very, very heartily endorse. And it doesn't contain a ton of that inscrutable math. It's very practical. So if you want to get into machine learning papers, it's a good way. The key insight that it shares is that we can learn by having the network of nodes share not data with the server, but only the model. I think the best way to illustrate how this works is to walk through what we'll call one round of federated averaging. So we start where the server has an untrained model, and the nodes have just their data, nothing else. Now, when I say untrained, it doesn't necessarily mean totally untrained. It means untrained on the data that it will eventually be trained on out there on the nodes. So we might seed this with, if we were building a language model from text, we'd probably seed it with BERT or Elmo or, some deep transfer, fine-tunable deep architecture. Or if, as a good data scientist, if you told me to build something for predictive text, I'd probably pull the Wikipedia data set and start adding my own text and hack something together. But the point is, it's only trained on proxy data. It's not trained on the data that actually lives out there on the nodes. So our server has this model, and it sends a copy to all of the nodes. And the nodes now also have a copy of that untrained model. And depending on how that's doing in train and test, we might actually start using it already, or we might not. But the nodes also have data on which they're trained to train their model, which the server does not. So they do so. And now every node has its own copy of the model that is like fit to the data on that node. So it sends it all back to the server. And the server has like n copies for n nodes of models. They're all different now. And the server combines the models by taking an average. That sounds crazy. And in fact, if you do it once, it doesn't work. We need to repeat this process a bunch of times. So we maybe do like a couple hundred iterations, maybe fewer, maybe more. There's some parameters you can tune. But the result is that the server now has a model that captures the patterns in the training data on the nodes, but it never had to see the training data on the nodes. So this like saves on bandwidth, because transferring models is usually a lot cheaper than transferring data. And it also increases privacy. So the server didn't see the data, and anyone listening in between also didn't see the data. So this is cool. Is that distributed learning solved now? Are we done? No, obviously. There were requirements of federated learning. So our chief requirement is that performance improves as we add more data. So we would probably do some like toy problem first, or like real problem but with proxy data. And we want to watch our performance curve as we add more data. And we can simulate that by basically artificially taking data away and seeing how it's going. If that's not getting better, then federated learning is unlikely to help. All it really gives us is access to the data on remote devices. The caveat is that we might get a greater data diversity on remote devices than our proxy data. So that's kind of a decision about how good your proxy data is and how likely it is to be drawn from the same distribution as your ultimate federated data. So we'd want to check that. The second requirement is that models can be meaningfully combined. So you can't take an average of everything. This isn't going to work with some fancy Bayesian non-parametric. It does work with a large class of models called neural nets. It also works like trivially with kind of linear logistic regression. You just take an average of the weights and this of the coefficients, and the same turns out to be true for neural nets. It works for kernel machines. It works for a useful class of models or subset of models. And the final requirement, which is non-trivial but getting better, is that nodes can train models. So this is not only predicting at the edge, this is training at the edge. And you can now do that on some fairly low-powered devices. Obviously, it's not as good as, you're not going to train your network as fast as training on 512 TPUs. But it does allow you to operate in a novel scenario. Okay, but if we meet those requirements, then the properties of such a simple algorithm as federated averaging are impressive. It works on non-IID data, that's non-independent and identically distributed, which means it works in the situation where I write quite a different kind of language than a teenager writes, and then my elderly relatives write. So the text data on my phone is like idiosyncratic compared to them, and that's fine. It also works with unbalanced data. I send far fewer texts than teenagers and probably my elderly relatives. So it's okay with there being like an imbalance of data on every node. It also works on massively distributed data, and I didn't realize this was a constraint, but it's outlined in the paper that previous approaches to distributed optimization, which is essentially what this is, kind of assumed that you had fewer nodes than you did data on each node. So you would have like maybe millions of examples per node and hundreds of nodes or something. And in this case, we can do it the other way around. So we can say we have like way, way more nodes than we do examples per node. And then finally, it works with limited communication. So we can't guarantee the availability of someone's smartphone or even of like maybe a remote device that's in a wind farm offshore or something. Fortunately, taking the average of like 9,999 models is not substantially different than taking the average of 10,000 models. So we're robust to limited communication. But working this stuff out is basically an empirical science. So people are doing tests and building stuff and seeing what you can trade off. So some of the things you can trade off are like how much compute you do on each round of federated learning. Do you train the network to convergence on each node and bring it together or not? The answer is no, but you can do more than one round. So previous attempts at distributed optimization were like, everyone go out, do one gradient update, everyone bring it back. And it turns out you can do more than that. So the report on which this talk is based came out at the end of last year, but one of my friends and colleagues, Ryan, had a little passion project, which is like, how non-IID are we talking? When we say the data can be idiosyncratic on each node, how much so? So we took MNIST, the classic computer vision problem, and we set up a simulated federated network where we basically just did it all on one machine, but didn't let the training data talk to each other. Excuse me. And we took a non-federated approach, and we got the classic MNIST results. I don't know how many nines of accuracy. The top graph is loss, and the bottom graph is accuracy. So we want the bottom one to be big and the top one to be small. And the blue line at the bottom, so the best line is non-federated. You can't really see the colors well. The next best line happens when we split the classes evenly and do 10% of each class on every node. So then we're basically training n copies of all the same thing and bringing it together. So then we went a little bit more pathological and said, what happens if we put 90% of a single class on each node and then split the remaining 10% equally? And it still gets 9 nines of accuracy. It just takes a few, maybe 50 rounds to get there. So then obviously we went fully pathological and said, what happens if we only show each node one single class? And it takes a lot longer to get anything useful, but it still gets to 80-something% accuracy in a slightly noisy way. And I think if we kept going for longer rounds, it would probably get further. And I thought that was quite remarkable. It's each network there that is being averaged has only ever seen a single class. It hasn't even solved binary classification. And by averaging them, we still managed to converge to something that is a useful discriminator. I mean, if useful means getting 80% accuracy on MNIST. OK, so that's what federated learning is and how it works. Let's talk a little bit about an application. So the application we built was called Turbofan Tycoon. It's available at that URL. Like I say, I'll be happy to walk people through it in more detail at coffee if you like. But the situation is this. We are a factory owner with turbofans that for some reason make money when they run. Turbofans turn out to be big jet engines. And they make us $250 an hour when they're running. And they occasionally fail. And when they fail catastrophically. So it costs us $60,000 to fix, and they're down for 60 hours. So that's bad. We don't want that. We'd like to maintain them so that we can maximize uptime and maximize profit. But maintaining them also takes them offline, and it also costs some money. So we have a kind of optimization problem where we want to trade off not letting them fail, but not over-maintaining them. So this is what's known as a predictive maintenance problem. And there are broad strokes 3 strategies. The first one is corrective. That's do nothing. That's let it fail and fix it. That's junk in this scenario. It's not junk if your cost of failure is very low. There's a relevant XKCD about throwing out machines from data centers when they fail and then throwing out the whole factory. But it's junk in this scenario because it's so costly when things fail. So the baseline, really, smartest thing we could do, or first order smart thing we could do, is preventative maintenance. And that's look at the distribution of when these things fail, pick the median or modal value or something, and say, intervene so many hours before that so these things don't fail as often. It's like your car manufacturer telling you to change the oil every however many miles. And that's a lot better. But it's not the best thing we could do. The real thing that we want to do is predictive maintenance. So we want to predict when the things are going to fail and intervene sufficiently before. And that's going to vary machine to machine and circumstance to circumstance. And within predictive, there are kind of 3 domains of data separation. So there's the first option is just to bring all the data together. That's obviously going to give us the best model. Federated learning is not going to beat that. But we're specifically talking about a circumstance where these machines are generating so much data that that's not really tenable. The bandwidth cost wouldn't be worth it. So we're going to rule out that scenario. OK, so then at the other end, we could just write a model on each device. We could just model each one separately. But then we only get the failure information of that device. And that's not going to be great. It's going to be better than nothing. So then the final strategy we can employ is to take the federated learning approach, where we share share models between devices. So we seed a model we bring one device worth of data to seed the model, send it out to all devices, learn, and repeat this over and over. And that will win. So the setup of the app is as a game. We are a factory owner. On the left-hand side, I'm going to orient you to this, not give a full demo. On the left-hand side, we have a bunch of information coming from our turbo fans. And critically, each fan has this scrolling bar along the top of it, each of the 4 fans. The red points are down, broken. Gray means good, making money, and yellow means down for maintenance. And on the right-hand side, you see we are the green top line in competition with a bunch of other factories. As you run the game, you will make money, and you will start with a default corrective strategy, and you'll be given the opportunity to upgrade to preventative, local predictive, and finally federated. And I guarantee you, even though this is a stochastic simulation, that you will win if you go to federated because it's just that much better. It's based on what's known as the CMAPS dataset, which is a dataset from NASA of jet engine failures. It is to predictive maintenance as, say, MNIST or ImageNet is to computer vision. So, like all things, especially in tech, federated learning is a point in a trade-off space. It's not some silver bullet that you should rush out and start doing. I'm going to talk about 2 classes of challenge that you'll encounter in building and designing and operating a federated learning system. And the first is systems issues. So I think CTO of Alkin, who are a healthcare startup doing federated learning for data sharing between health-related institutions, or rather model sharing, they describe federated learning as a stress test of your engineering culture because it crosses so many team boundaries. You need to have like literal algorithm experts building the jet engine, so to speak. You also need to have people who are looking at network communication, and we need to have people who are building the infrastructure to run this. And I'll advocate that you need to have people thinking about the social consequences of what you do. It's not trivial to deploy. And we'll talk about open source tooling in a bit. But this is way harder than the problem that most of us face, which is getting our sklearn model from a Jupyter notebook into an EC2 server that we have direct access to. But let's say that we can do that, and we can build a system. Maybe the first thing we need to talk about is power. So training a model requires power, and it requires power on our user's device. This is what we euphemistically say, tapping unused edge computing resource. We mean making our users pay for our training regime. So we need to have a discussion, or at least set an expectation, that maybe we'll only train on your mobile phone, taking the example of mobile phones, at night when it's plugged in, between certain hours. And that'll help. It actually turns out, though, communicated in the right way, this is a win, because transferring the data is more expensive often than transferring the model multiple times and training. So done right, federated learning is a win for power consumption. Okay, so maybe the next thing is drop connections. We initiate a round of federated learning, and we request a model back from however many nodes. Rarely the whole set of nodes, maybe like some subset of our nodes. And some of them just aren't going to return. So we need to be robust to that. We can't just hang on everything returning. And that's easy to do with averaging. We could set a threshold at, say, when 70% of nodes return. We'll just close the round then and then do it again. And that would work if it weren't for stragglers. So the other thing is that some things will return, but we may close our round before they do. And here we have to be really careful about pathology. So I saw this, I'm going to come back to the slide, but I saw this tweet just a couple of days ago by someone called Elliot Andres from artisans.ai. They did a benchmark across 5 Apple devices on some image, I think it was like image segmentation or something. How many images did they process per second? And it turns out the iPhone 6, still in use, does 2.4 images per second, and the iPhone 11 does 21.34 images per second. That's just inference. That's just predicting. But let's assume that similar performance characteristics hold for training. So then the stragglers are always going to be the old phones. And suddenly, your language model is only learning from people with an iPhone 11. So you're seemingly in like technical network communication issue just embedded social injustice into your language model, or social inequity at least. I don't have a silver bullet for that. We just require people to think hard about it and behave responsibly. Privacy. So the second class of issues we'll talk about alongside systems issues is privacy. Now, I've waxed lyrical about how much of a win for privacy federated learning is, so let's talk about that first. Who here has dealt with the GDPR? Yeah, as have we all. So paraphrased, the GDPR says that data must be collected for a specific purpose, and the user must have consented to it, and it must be necessary to achieve that purpose, and then you have to get rid of it. I like the slightly pithier version, which is data. Don't collect it, don't store it, don't keep it. This comes from Maciej Czeglowski's really, really excellent Strata talk in 2015, Haunted by Data. It's 20 minutes long, just go watch it. So federated learning seems to be a win from this perspective. Like, we've moved from the model of data lake to like many data puddles. But it's not a panacea. So while we're transferring data from a node to a server, the server no longer has access to the data, but it does have access to the model, and any adversary in between does have access to the model. And the adversary could be inside the organization. Maybe it's not even like a sort of adversary to say some dude with a balaclava and a laptop. It's like just some ill-thought-out use case. And we can't inspect the data, but we can inspect the model. And this puts us in an unusual circumstance where a tool that, like, those of us who are concerned about ethical applications of machine learning strongly advocate for, which is like interpretability tools, becomes an aid to an adversary, because you can now start understanding what people are doing just by looking at the model. So say you have some language model, it will have a set of weights associated with the word muffin. And if I see those weights change on an update, I know that my user is talking about muffins. More scarily, there was this 2017 paper, Deep Models Under the GAN, that managed to reconstruct. It wasn't on a federated learning setting, it was on something called a collaborative learning setting, but it's a very, very similar setup. The image on the left belongs to some node on the network, and the image on the right is reconstructed on a separate node that did not have access to the data on the left. If I was that person, I'd feel like my privacy had been violated. And it's just an insanely clever attack. So the way it works is to join the federated network, which is something that feasibly you could do in a commercial setting, legitimately, and then use the model that is sent out by the server as the discriminator in a GAN setup, an adversarial training setup, and build a generator to target one of those classes. So far, that's just like a classic what's called model inversion attack. You're trying to work out like the training data that was used to train a model. But it's cleverer than that, because by targeting a single class, you make it hard for the network to discriminate between your fake classes and the class on some other user's device. And so it has to work harder, and the network weights adapt to extract more information from the true image to help distinguish with the fake class. So this is just like level clever. But I think what it really illustrates, and there's been a bunch of follow-on papers too, and there are things we can do to try and mitigate this. I think what it really illustrates is that privacy is an ongoing responsibility. There's no like, oh, now we're private. And that really, actually, we shouldn't have been surprised by this. So our operational model changed, like where we kept data and stuff changed. Naturally, our attack surface changed. Okay, so you're not put off by the fact that privacy is not going to be like silver bullet solved by this thing, and you think you have a good enough engineering culture to build a federated learning system. How? So I'm going to talk briefly about two tools, both open source. The first is OpenMind. OpenMind self-describes as an open source community focused on researching, developing, and promoting tools for secure, privacy-preserving, value-aligned artificial intelligence. That's way more than federated learning. They run two open source projects, PySift and Grid. Grid is a peer-to-peer platform for decentralized data science. That's like how you get your things to talk to each other. It runs on the IPFS called the Interplanetary File System. Pretty cool name. PySift is a library for privacy-preserving deep learning. So that is not only federated learning, but it does have a federated learning implementation written in PyTorch. It also includes like secure aggregation and multi-party communication, I think homomorphic encryption. It's a non-goal of OpenMind to just build a federated learning library. So the next project I'll briefly talk about is TensorFlow Federated. I think there are plans to incorporate that into OpenMind as well. So they're happy just taking tools where they exist. The point is to build exactly what their mission statement is, which is a means of doing secure, privacy-preserving, and value-aligned AI. So the second thing to look at is TensorFlow Federated. This was announced at the TensorFlow Dev Summit in March this year. And it has two parts. It has a federated learning API, which is like a high-level, lets you wrap your Keras model in federated averaging, say. And they seem to have paid like particular attention to separation of concerns. So if one of us were to just start hacking away on a federated learning system, it would very quickly, without strict discipline, become like a total mess because you're mixing up like how you update your model with how you communicate with updating your model, and it's very like it really entwines systems engineering and machine learning. They seem to have paid like really good attention to these separations of concerns in such a way that means that people with different expertise can contribute to the project meaningfully without having to understand it fully, like in full depth, absolutely every other part of it. And that is all built with the second part of the library, which is the federated core API, and that's a set of low-level interfaces for building novel federated learning algorithms, so things to replace federated averaging. Maybe you want to include some like secure aggregation in the procedure, or maybe you want to only accept an update if it hits some performance metric on a held-out test set on device or something. The bad news is, as of right now, it only provides a local simulation runtime. I think the intention is to allow other runtimes to be built. I don't know whether like TensorFlow itself, the core team are going to build them, so that the API basically doesn't change. You can like write your federated learning algorithm with a simulated runtime and then deploy it to devices in the wild. So it's new but promising. There were a few other open source things like WeBank put something out. I've not really looked at it. I think I would comment on both of these previous projects that I have not contributed to either, but I did take a look through their GitHub repos, and they both seem like very welcoming communities. They have well-tagged issues for new contributors, so if you're new to open source or want to start contributing to something, they seem like good places to go. And with that, I will summarize. So federated learning is machine learning on decentralized data. All the buzzwords. And you might have a use case if privacy is needed, but you're going to have to work harder than just federated learning. If bandwidth or power consumption are concerns, that's to say the bandwidth and power consumption of transferring data. If there's a high cost of data transfer in general, if there's, for some reason, there's a high cost associated with data transfer, but you have some requirements, like you need to know that your model's improving with more data and some of the other criteria that we outlined earlier. Like, so for example, natural use cases seem to be predictive maintenance and industrial IoT, smartphones, healthcare. You can imagine maybe this is useful for people who are on drug trials and you want to monitor biometric signs, but that's obviously intensely private data. And then we use like enterprise and corporate IT as an example. Basically, we're talking about somewhere where there are silos who, for privacy reasons, can't talk to each other. If you're interested, there are a bunch of blog posts. These slides will be made available, I'm sure. Some from us, some from other places, and then there's some papers. And the two that we highlight in blue, one was the paper I talked about earlier, Communication Efficient of Deep Networks from Decentralized Data. That's a good intro. And then the second is a generic framework for privacy-preserving deep learning. That is the PySift paper out of OpenMind. Both worth a read. So thanks. I hope it's not considered uncouth, but if you are a smart person who is kind and cares about responsible and effective use of AI, and can also code, and if by some miracle you also know Kubernetes, but that's not a strict requirement, I am hiring.